Okay, so now we're going to do some examples using L'Hopital's rule. I promised you a very brief bio of L'Hopital. He's a 17th century French mathematician. He was a student of Bernoulli, who you may have heard of, Bernoulli equations if you're in engineering or physics majors. So there you go, L'Hopital. If you see pictures of him, he's got the big powdered white wig. Looks a lot like Sir Isaac Newton, at least to my untrained eye. So let's try and use L'Hopital's rule in using a couple of equations, using a couple of examples. And we'll start by going back to that equation that I've used for the past couple of pages. So we're talking about the long-run behavior of this function. And that means we want to consider the limit as x goes to infinity of this function. We'll also do it with as x goes to negative infinity. So if I just try and evaluate this without using anything fancy, just plugging in x goes to infinity, what I get is infinity over infinity, which means this is a candidate for using L'Hopital's rule. I get to apply this theorem up above. So okay, it says I take the first derivative of the top, the first derivative of the denominator, and try the limit again. First derivative of the top is just 1. First derivative of the bottom is 2x. I try and evaluate the limit again. This time I get 1 over a very, very large number, which is 0. So this is evidence from that previous problem. Let's see if I can find that. That says as x goes off to infinity, my limit gets increasingly closer and closer to 0. You can imagine doing the same thing, trying this with negative infinity. Again, I'd get negative infinity over negative infinity. So I'm a candidate for using L'Hopital's rule. I take the first derivative of the top and the bottom. I get 1 over minus 2 times negative infinity. Once again, that approaches 0 from the negatives this time. So this sort of backs up that sort of picture. So there's a very simple, straightforward example using L'Hopital's rule. The point is, yes, as you take the limit, this goes to infinity, this goes to infinity, but notice this is an x to the first power, this is an x to the second power. As x gets bigger, this gets bigger much faster. Its rate of growth is significantly larger than the rate of growth of that. So we're just going to burn through a couple of examples real quick just to help cement this into your head. Let's do another fairly straightforward quadratic. I said quadratic. I meant a quotient. Sorry about that. So once again, if I try and just evaluate this, I'll get infinity over infinity, an indeterminate form, so that means I'm allowed to use L'Hopital's rule. Take the first derivative of the top, take the first derivative of the bottom, and attempt to evaluate this limit. And once again, I got infinity over infinity. That's okay. I still have a limit that goes to an indeterminate form. So once again, I get to apply L'Hopital's rule. There are circumstances where you end up using L'Hopital's 2, 3, or more times. So I'm just going to do L'Hopital's rule again on this equation. First derivative of the top. First derivative of the bottom. And as I try and evaluate it, as x goes to infinity, I get 2 over a really, really large number. This goes to 0. So once again, if I were trying to graph this equation as x goes off to positive infinity, I expect to have a horizontal asymptote where it approaches 0 but never quite gets there. I could play the same trick and take this limit as x goes to negative infinity. I'd still get 0, but this time I'm approaching 0 from the underside, from the negatives. So there's another straightforward example with a quotient function. Let's try something slightly more complicated. Now, notice L'Hopital's rule doesn't say that you always have to be evaluating the limit as you go to infinity. Sometimes you're curious about what happens at a potential hole in a graph. For instance, if we were looking at this function, now this is the sort of function we talked about in the very, very early days of the class, where clearly we've got a hole in the graph right where x equals 0. And in fact, we've got tangent of x over x. If we try and evaluate this limit directly, we get 0 over 0, one of my indeterminate forms. So I'm allowed to use L'Hopital's rule. So we don't really know what happens when x equals 0. But we can find out what happens as we get really, really close to 0. Now again, in the early stages of the class, you were using GeoGebra, you were making a little spreadsheet table, and you were just picking values of x that were increasingly closer to 0. You would try 0.1, 0.01, 0.001. L'Hopital's rule now gives us another technique for answering questions like what happens as I get really close to 0, but not exactly at 0. So I tried to evaluate it. I got an indeterminate form. I'm going to apply L'Hopital's rule. Take the first derivative of the top. The first derivative of tangent is secant squared. Derivative of x is 1. Evaluate this as x goes to 0. Secant of 0, let's see, secant is 1 over cosine. Cosine of 0 is 1, so that's 1 over 1, 1 squared. I get 1. And I won't bother doing it here, but sure enough, if you graph tangent x over x, you do have a little hole right at x equals 0, but from both sides as you approach that hole, you're going to be getting very, very close to a y value of 1. Let's rip off one more. So here's another quotient, and we can dive straight into using L'Hopital's rules. So I'm going to take the first derivative of the top and the bottom, and this was a trick question. I'm evil that way. Notice what I did not do was attempt to evaluate this limit at the very beginning. If you had, you would have noticed I would have gotten a 0 on the top. I'm sorry, 0 plus 1. I would have gotten a 1 over 0, which is not one of my indeterminate forms. You do not get to use L'Hopital's rule. All you can say about this one is does not exist. So just a reminder, you have to do this test before you go on to that. And I hate to end on a downer, so let's do one more example. I've got a little bit more space on the page. Okay, let's try and evaluate this limit. If I plug x equals 2 into this, I get e to the 2 squared, so that's e to the 4th minus e to the 4th, 0. 2 minus 2, 0. So I get 0 over 0 in indeterminate form. Yay, so I can use L'Hopital's rule. If I take the first derivative of the top, so the first derivative of e to some junk is e to some junk times the derivative of that junk minus derivative of e to the 4th, that's just a constant, so this just goes away. Derivative of x is 1, negative 2, that's a constant, that just goes away. And so now it looks like I've got something that I can actually evaluate the limit of as x goes to 2. This is 2 times 2 is 4 times e to the x squared So if we attempted to graph this function, it would clearly have a hole at x equals 2, and yet we know approaching that hole we're going to get to y values that are very, very close to 4 times e to the 4th. So those are some examples using L'Hopital's rule. I hope that made sense.